Hello guys, welcome to Amazing Engineering, and today in this OpenFOAM tutorial we will see how to set any transfer case considering a circular fin. Fins are devices used to increase the heat exchange surface of bodies. Normally in real applications we use a series of fins, but for our case a singular fin is enough. So let's create our work directory. I called it circular fin, and for the geometry, because it is more complicated than the other cases, we will use the design software SolidWorks. Before creating the geometry, we have to pay attention to our coordinate system, because we have to use the same coordinate system used by ParaView. That's because if we use a different coordinate system, our boundary conditions could be inverted in ParaView. So ParaView coordinate system is like this. So this is y direction, this is the x direction, and then the z direction. And according to this coordinate system, we will create the first sketch on the right plane. Our body has a rectangular surface. This segment is 400 millimeters length, and this one 200 millimeters length. Close the sketch and click on Extruded Boss. Our extrusion is 30 millimeters length. Now we have to create the circular fin on the surface. So let's create a sketch on the surface. Let's create a circle, and its diameter is 100 millimeters length. Close the sketch, click on Extruded Boss again, and this extrusion it is 400 millimeters length. So this is our domain, and now we have to export it as a step file. So let's go to Save As, set step file in file format, and we can save it on desktop. Close SolidWorks. Now let's go to Salome in Geometry field, set millimeters in file properties, and now we have to import our geometry file. So let's go to File, Import, Step File. Select our file, click on Yes, and this is our domain. We can call it circular fin. Now we have to create the graphs for the boundary conditions. So let's go to Create Graph, select Face Graph, and the first one is called Dot Part. And we have to select this surface. The second one is called Part, and we select the end face. And the last one is called Frontier, and we select the other surfaces. Apply and close. Now let's go to Mesh field and create a mesh selecting the domain. So click on Create Mesh. Let's call it circular fin. Let's set NetGen 3D, and in hypothesis we set NetGen 3D parameters. We set 0 as minimum size and 0.02 as maximum size. Click on OK. In 2D part we set NetGen 1D 2D, and as hypothesis we set NetGen 2D parameters. Again, we set 0 as minimum size and 0.02 as maximum size. Apply and close, and compute the mesh. So our mesh is composed by around 3000 volumes. Now let's import our graphs in the mesh. Click on Create Graphs from Geometry and select all the graphs. Apply and close. Now we can export our mesh as a UMV file. We call it circular fin, and we save it in our work directory. Now let's close Salome. Let's go to our work directory and open a Bash and Ubuntu window. Now we have to reach our work directory, so change directory mnt c users admin desktop circular fin. And now let's write the command ideas UMV2FOAM, selecting the mesh file. Let's go to constant directory, polymesh directory, and in boundary file we have to set the type of boundary conditions. For this case, we set a wall type boundary condition for all the graphs. G file is the gravity acceleration, and its value is minus 9.81 meter on second squares along y direction. In turbulence properties we set a laminar flow, and in physical properties we have to set the thermophysical properties of our fluid. In type setting here raw thermo, we are saying that the thermophysical properties are based on the fluid density. With per mixture, we are saying that our fluid is not the result of a combustion process. Transport include fluid properties like dynamic viscosity, thermal conductivity, and thermal diffusivity. If we set const, we are saying that Prandtl number and dynamic viscosity are both constant. In thermo, we have to set the type of thermodynamic model. With H constant, we are saying that our thermodynamic model is based on a constant specific heat. We can set perfect gas equation as equation of state. With space, we have to set the parameters of the space, for example, number of moles and mole weight, and with sensible enthalpy in energy, we are saying that there is no internal heat formation. Now, in mixture we have to set some parameters of the fluid. In this case we can use air as fluid, so we set one number of moles. 28.96 has mole weight, has specific heat of 1007, 0 has fusion temperature, and the Prandtl number and the dynamic viscosity of the air. Let's go to 0 directory and set the boundary condition of the physical properties. So in velocity file we set no slip boundary condition for all the graphs. In temperature file we set 0 gradient boundary condition for the frontier, the value for the hot part, and about the cold part we can choose between two different boundary conditions that depend on the type of fin we are using. For example, if we consider a fin with an infinite length, the temperature of the cold part, so the extremity of the fin, will be equal to fluid temperature, while if we are considering a fin with an adiabatic extremity, we will set a 0 gradient boundary condition. For our case, we can consider a fin with an infinite length, so we have to set a fixed value boundary condition. In pressure file, we set calculated boundary condition for the all graphs, and the initial value is 10 to the 5 megapascal, and at the end, PRGH file represents the dynamic pressure. We set a fixed flux pressure for all the graphs, and it means that we are setting the value of pressure gradient, and in this case it is 0. Now let's go to system directory and let's set simulation parameters in control dict. So our solver is buoyant simple foam. We set 0 as start time, 150,000 as end time, a delta t of 0.5 second, a write interval of 1000. We set 1 as put write directory, and at the end of the file we can find the functions include residuals, and it allows us to watch the residuals during the simulations. Residuals represents the differences between the numerical solution and the analytical solution. In order to have the best solution, we want them to be as small as possible, so we have to set their values in FV solution file. Now, residuals value depend on the case you are analyzing. I suggest you to set as a start value the smallest one, for example 10 to the minus 4 or to the minus 5, 7 and so on. So you can watch the residuals during the simulation and you can know if their values are good or not. Thanks to residuals we can know if simulations is converging or not. Now let's start the simulation, writing the solver buoyant simple foam. In order to watch the residuals, we have to open another version of Ubuntu window and reach the directory. So change directory, mnt, change directory, nt, c, users, admin, desktop, circular fin, and we have to write the command foam monitor -l post processing residuals 0 residuals point that. Click enter. And these are our residuals, so we can know if solution is converging or not. Now that the simulation has finished, we can open ParaView with parafoam command. Click on apply, set temperature and play the simulation. So this is the temperature along the domain. But if you set velocity, you notice that its value is 0 along the whole domain. But if we create a clip and we choose the opposite direction of z normal, so we have to set -1 in normal value, we notice that the fluid is moving from the hot part to the cold part. Okay guys, this is all for today. I invite you to subscribe on my channel and see you for the next video.